Number 14, part A. So very back page. When I look at 14, part A, I notice that it looks like two shapes that have been stacked on top of each other. What two shapes look like they've been stacked? Trapezoid and a rectangle. So we are going to need the area of both of those, and we are going to add them together. Trapezoid plus area of a rectangle. How do we find area of a trapezoid? Close. 1/2 base times height, but how many bases do we have? Two bases, so we have to add them together. So 1/2 height times base 1 plus base 2. And then onto that, we need to add the rectangle bottom. How do we find area of a rectangle? Length times width. All right, so let's look at this trapezoid. Do we have the height of the trapezoid? 4 inches, yes. It's making a right angle with that bottom base, which is how I know this is the height. So that's what we're going to put in for H. How big are the two bases that we're going to add together? 13 is one of them. 24, because it is congruent to the other side of that rectangle. So base 1 is 13, base 2 is 24, or vice versa. Make sure you add those bases. All right, now let's look at the rectangle. Length and width on this rectangle. What's the length and the width? 24 is one of the ways. So let's go ahead and call that the length. So that means I need the width, which would be this dimension here. How can I find that? 15 minus 4. 15 inches minus 4 inches, which makes it how big? 11 inches for our width. All right, now we got to stick this into our calculator. 1/2 times 4 times 13 plus 24. What is 1/2 times 4 times 13 plus 24? 74. So I do 74 plus whatever I get when I multiply 24 and 11 together. $264. Now we add those two together. We add our trapezoid and our rectangle. You should get 338. Do we need units with that? Inches squared. Yes, thank you, sir. All right. What else would you guys like to see? Number 11? Absolutely. Number 11, there are several features that we need to just identify from the picture. So we're going to name them. If it's a segment, we'll write the name of the segment. If it's an arc, we'll write the name of the arc, angles, so on. For these 4, we're going to go on and find the measurement of those, because we can actually calculate how big that is based on the information they've given us in our picture here. So I have a hexagon, which has how many sides? 6 sides that's been inscribed inside this circle. So we're looking mainly at this hexagon right here. Why do you think they've shown it to me inscribed inside of a circle? It's so I know all the sides are congruent. This is one of the ways that they're showing me that this is a regular hexagon. All 6 sides are congruent to each other. If they weren't all the same size, I couldn't fit it perfectly inside of a circle like this, where all the points, all the vertices, all the corners are on that circle. So I have a regular hexagon here. We want to name a radius. Now in a circle, a radius goes from the center to the edge of the circle. In a polygon, the radius goes from the center to where? To a vertex, yes. center to a corner. BG or AG, either one of those would work. So what's different about the apothegm then? Thank you. Radius goes from center to corner. Apothegm goes from center to side. There's only one apothegm that's drawn in this picture. HG or GH. Minor arc. A minor arc is any arc that's less than 180, but when I'm looking at a polygon inscribed inside of a circle, the minor arc that I'm mainly interested in is between two adjacent vertices, like between A and B, or B and C, or C and D, two vertices side by side. So I'm going to go with AB for this one. Remember, minor arcs, we only need 2 letters, but you do need that arched symbol over the top so that we know we're talking about an arc and not a segment. Measure of that minor arc. Each of the sides of my polygon is a chord of my circle. It goes edge to edge, but it doesn't go through the center. How many congruent chords do we have? 6 congruent chords. So we're taking our circle and we're cutting it into 6 congruent arcs with those chords. So the way I find the measurement of that minor arc, we're going to do 360 degrees, that's all the way around the circle, divided by, in this case it would be 6, because I have 6 sides on my hexagon, or 6 congruent chords here. 36 divided by 6 is 60, so the measurement of my minor arc is 60 degrees. Major arc, now I want more than 360. The easiest way for me to get a major arc, I'm going to use the same 2 endpoints, A and B, but I'm going to go the long way around the circle, like this. To make sure that my reader knows that they need to go the long way around the circle, we need 3 letters. I need my endpoint, so A. Then I need one of these other points so that they know to arc this direction and then end up at B. So AFB or AEB or ADB, just so you know you're going this way. So I'm going to call this one AEB. Still need that arch over the top, my arc symbol. And I've got pretty much the whole circle here, except for that minor arc. And we said that minor arc was how big again? That's 60 degrees. So what would I need to do to find this major arc that is everything except that? We're going to subtract it. 360 minus the little bite that we're going to leave out. So 360 minus 60 gives me 300 degrees. Central angle. This is an angle whose vertex is at the center of the circle. It's at the center of our polygon. There's only one that they have drawn here, right here. AGB or BGA. How do we find the measure of a central angle? $360 divided by the number of sides. So 360 divided by 6 gives me 60 degrees. So this angle right here is a 60-degree angle. And that makes sense and is consistent with what we said about this minor arc earlier, because a central angle is the same size as the arc that it intercepts. They have the same measurement. So if my minor arc right here is 60, then my central angle that intercepts, it has the same endpoints there, has to be the same size. Inscribed angle. An inscribed angle is an angle whose vertex is on the circle. So I'm going to look at this one right here. Angle BAG. the measure of that inscribed angle, I'm going to look at this right here to help me figure this out. What have I just highlighted? A right triangle. That apothem is coming and making a right angle with the side. So I'm going to redraw that right triangle off to the side a little bit, or actually underneath. So there's my apothem. Here's that radius. And then here's half the side of the hexagon. There we go. I know that this is a 90-degree angle because it's a right angle. I know the measure of my central angle is 60 degrees. What's the apothem doing to that central angle, though? It's bisecting it. So how big is this angle right here? 30 degrees. Because that's 60 cut in half. And so what I want to do here is find this angle. What do we know about the three angles in a triangle? They add up to 180, so I'm going to do 180 minus, and then I'm going to put those other two angles together. That's a 90-degree angle and a 30-degree angle. What's 90 plus 30? 120. And 180 minus 120 would give me 60. So something I want to point out before we go on to part G. The minor arc and the central angle are the same size. That's not an accident. That's not a coincidence. That's always going to be the case because that central angle is intercepting that minor arc. The inscribed angle being the same size as these two, that is a coincidence on this problem. That is only because we have a hexagon here with 6 sides. If I had a pentagon or an octagon or a decagon or anything else, this inscribed angle would not have the same measurement as my central angle. Those would be different. All right, last thing to do on this problem, we want to write a congruence statement for the two congruent triangles pictured in the figure. Well, one of those two triangles I've colored in yellow. The other triangle is this guy right here. So I've got a yellow triangle and a pink triangle. And I need to write a congruence statement for those. It doesn't matter the way I name the first triangle. The second triangle, I have to be careful to match up the corresponding congruent parts. Why don't we name the yellow one first? What name could I give to that yellow triangle? A, G, H. Because remember, that's G. I just covered it up with all of my drawings. So A, G, H, yellow triangle. AGH is congruent to, and now we're going to write the name of the other one. What'd you say? BGH. Angle B is congruent to angle A. Those are both inscribed angles. Angle G. You said number 12? Number 12 next then. Find the area of the triangle. What's our area formula for a triangle? 1/2 times base times height. What relationship do the base and the height have to have with each other? Has to make a right angle. They have to be perpendicular. A base has to be one side of my triangle. So I could use this as the base because I know how big it is. If I use that as the base, though, this would have to be the height. Do I know how big that is? No. I don't even know how to find that because I don't know how big this is. I don't know how big this is, so it's not like I could use Pythagorean theorem. I could use this as my base because I also know how big that side is. But if I use that as the base, then this would be my height. And I've got the same problem. I don't know how big this is. I don't know how big this is. I don't know how big this side is. I'm not going to be able to use Pythagorean theorem to find that height. Do I have another area formula for a triangle that I might be able to use here? Yes. 1/2 AB times the sine of C. A and B have to be sides of the triangle. Do we have numbers that we could put in for A and B? Yes, we know exactly two sides on this triangle. We have an 18-foot side and a 26-foot side. So I'm going to start subbing in A equals 1/2 times 18 times 26 times sine of angle C. Angle C can't just be any old angle in that triangle. When I'm looking at this formula, the proper way to read this is two sides of my triangle and the angle in between those two sides. So this is the angle that I need right here. And I run into yet another problem because I don't know that angle. Yes. We could do 180 minus the two angles that we do know, 74 plus 44. What is 74 plus 44? 118. And 180 minus 118 would give me 62 degrees. So this angle here is 62. That is what we put in for angle C. So now I can grab my calculator. I can do 1/2 times 18 times 26 times sine of 62 degrees. And you should get an area of approximately 206.61 feet squared. What else would you guys like to see? 13? Absolutely. Find the area of the shaded region. Is this whole figure shaded? No. What shapes do we have going on? Circle and a triangle. Which one is the whole, the thing that we would want to subtract because it's not shaded? The triangle. So we're going to do the area of the circle minus the area of the triangle. How do we find the area of a circle? Not circumference. Pi r squared. So pi r squared minus, how do we typically find the area of a triangle? 1/2 base times height. Let's see if we can use that here. Otherwise, we're going to have to do the 1/2 AB sine C. What relationship do the base and the height have to each other? Perpendicular. Has to form a right angle. Do I have a base and a height for this triangle? Pieces that are perpendicular. Yes. Because I have what kind of triangle here? I have a right triangle here. So what should we use for the base and for the height? 8 and 6. Doesn't matter which one you put where. What is 1/2 times 8 times 6? 24. So I need to find the area of the circle, and then I'm going to minus 24 from it. What do I need to calculate the area of the circle? I need the radius. Do I have the radius? No. But I do have this that I could find, because that's the hypotenuse of my right triangle. What part of a circle would we call that? That's my diameter. And why do I care about that? Because it's, yep, the radius is 1/2 of my diameter. So this segment and this segment would be the same size. Those would both be radii. So let's find our diameter. A squared plus b squared equals c squared. The hypotenuse is the thing that I have labeled as d, as the diameter of my circle. So I'm going to put d in there. So what should go in for a and b? 6 and 8. So I have 6 squared plus 8 squared. What is 6 squared? 36. And 8 squared? What is 36 plus 64? So 100 is equal to my diameter squared. How do I get rid of the squared part? Square root. That gets rid of the squared on my d. Squared and square root cancel. What is the square root of 100? 10. So the radius is 5. Because the radius is the diameter divided by 2. My diameter is 10. 10 cut in half is 5. And that would have the unit of centimeters on it. So that's what we're going to use in the place of r. So I have pi times 5 squared. And I want this in its decimal form so that I can subtract 24 from it. 78.54. And then I minus 24 from that. And I get an answer that's easy for me to remember because I've been doing this all day. Should get 54.54. What kind of units should we put with that? Centimeters squared. There you go. You had the squared part right. Yes. If you're taking the test and you put units on your answer and make me happy, but you accidentally put feet instead of centimeters, sorry, will I take off points? No. I'm not going to take off points for something like that. That would be a transcription error. That would be you did all of the work with the math part right. You just recopied the units wrong. I'm not going to take off points for something like that. What else do you guys want to see?
D,
14. 14D, absolutely. So back to that back page. 14D. I've seen people approach this problem a couple different ways. You could look at this as a giant rectangle with these two triangles subtracted out from it. Or you could look at this as different shapes put together. If you look at it as a big rectangle that we take out those little triangles, then we're going to subtract pieces. If you look at this as different shapes put together, we will add them together. I kind of like that way of doing it better. I think that way is a little bit easier. Certainly with the information that they've given us, it's going to be easier to calculate. I need to make sure that I'm finding shapes that I know the names of. What's a shape up there that you see that you know the name of? I see a triangle right here. And then I've got this guy. I don't have a name for that, but could I cut it into shapes that I do know? I can cut it into two rectangles if I cut it this way. Or I could cut it this way, and I could cut it into a rectangle and a square. So here's my rectangle. How do I know that this bottom piece down here is a square and not just another rectangle? Yeah, 4 feet, 4 feet. Base and height are the same, so the opposite sides must be congruent, so all 4 sides are 4 feet. All right, so we have our area of a triangle plus the area of the rectangle plus the area of the square. How do we find area of a triangle? 1/2 base times height. What about rectangle? Length times width. And a square? Length times width, or because my length and width are the same, you could say side squared. You're going to get the same answer if you do length times width, so you don't have to memorize side squared because it gives you something different. If you like to think about squares as length times width, you are perfectly fine. You'll get the same answer. How big are the sides of this square? 4. So I've got 4 squared. which is how much? 16. All right, now let's go look at that rectangle. I need the length and the width of the rectangle. What are the length and the width? 9 is one of them. How big would this side be? 2. How did you get 2? 6 minus 4. We know that this side right here is 4. So this would have to be 4 feet to make it congruent with the opposite side. So up here I would have 6 feet minus 4 feet, which would give me 2 feet for, I'm going to call it the width. You can call it the length. It does not matter. So I'd have 9 and 2. 9 times 2 is 18. I just have that triangle. I need the base and the height of the triangle. I don't have any numbers on my triangle. Can I find the base, this side of my triangle? Yes. 9 minus 4. We know that the entire thing, edge to edge here, is 9. And we know that this side of the square is 4 feet. So I do 9 feet minus 4 feet, and that gives me a base of what? 5 feet for my base. All right, so it's 1/2 times 5 times whatever my height is. From base to tip, here's the height that I'm looking for. 4. How did you know? You're absolutely right. Because of the square. The tip of this triangle goes down exactly as far as my square. So it has to have the same length as my square. So 4 feet. What is 1/2 times 5 times 4? 10. So now I add those all up. 10 plus 18 plus 16. And I get 44 feet squared. What else do we want to see? 14, which one? B? Absolutely. What kind of shapes do I have here? Pentagon and a circle. Which one's bigger? Circle is bigger. So we're going to do the area of our circle minus the area of the pentagon. Area formula for a circle is what? Pi r squared. Minus my pentagon. I don't have an area formula that's only for a pentagon. It's a regular polygon. So 1/2 apothem times perimeter. See if we can do the circle first. Do we know what the radius is? 6. So pi times 6 squared. Let's do the easy part. What is pi times 6 squared in its decimal form?
113.
Yep, or 0.097 if you take it out to 3 decimal places. I don't remember what the directions say on this. There we go, hundredths. So we need to go to at least 2 decimal places. That would round to 113.1 if you did to the nearest hundredth. I'm going to take it out to 3 for right now. All right, so for my pentagon, I need both the apothem and the perimeter. Do I have either one of those? No. So we're going to have to find it. First thing I would do is come in here and draw in another radius. Because then I can use that to find my central angle. How do we find the measurement of the central angle again? 360 divided by the number of sides. We have how many sides? 5. What is 360 divided by 5? 72. So this angle right here is 72 degrees. All right, let's draw in that apothem. Goes from the center to a side, and it makes a right angle where it hits that side. I'm going to take this right triangle right here, and I'm going to draw it larger off to the side so that I can look at it a little bit better. So here's my apothem. Here's my radius. And this is half of the side of the polygon. So there's half the side. This is the apothem. And we know how big the radius is. That is 6 centimeters. What is the apothem doing to the central angle? It's cutting it in half. It's bisecting it. My central angle was 72 degrees. So how big is this angle? 36, because that is half of 72. We are going to stand right at that 36-degree angle, and we're going to label the sides of our triangle. This is the hypotenuse of my triangle. Over here where it says half the side, because that's half the side of the pentagon, I'm going to label that as my opposite side, because I would have to walk through the triangle to get over there. And then the apothem is my adjacent side. Let's find that apothem first, since that's the first thing my formula asks for. Formula is 1/2 times the apothem. I don't know how big that is, so I'm going to leave space for it. So I want this. I have this. I know that's 6 centimeters. So, TOA, adjacent and hypotenuse. Which of these three will let me use adjacent and hypotenuse? Cosine. So cosine of 36 degrees is equal to the apothem divided by my radius, which is 6. So then I'm going to multiply both sides by 6 to cancel out that denominator. Then I grab my calculators. I do 6 times the cosine of 36 degrees. .854 is the size of my apothem. So that goes in my first set of parentheses, 4.854. And now I need the perimeter. Well, if I'm going to find the perimeter, they didn't give it to me, I need to know how big one of the sides of the pentagon is. I can't find the length of a whole side, but I can find the length of half a side. So now I don't want the apothem anymore. I want this. Which one of these lets me use opposite and hypotenuse? Sine. To use tangent, I would have to use my apothem, which I have a number for that, so I could do that, but I always like to go back to my given information and use that. All right, so I have sine of 36 degrees is equal to, we've got our half side over the radius of 6. Thank you. Let's scoot that out just a little bit. So now I'm going to multiply both sides by my denominator of 6 to cancel that denominator out. So 6 times the sine of 36 degrees, 3.526, equals half of a side of my pentagon. So how do I find the whole side? Multiply it by 2 or add it to itself, yes. 2 times 3.526. So one side of this pentagon is 0.052? So how do I find the perimeter now that I know that? multiply it by 5. Number of sides times the length of one side. 5 sides times 7.052. That is 35 point what?
Wait, 26.
35.26. Perfect. So this is what we need here. 35.26. Now I can finally calculate the area of that pentagonal shaped hole. I do 1/2 times 4.854 times 35.26. I get what?
$85.576.
85.576. So now we subtract those two. 113.097 minus 85.576. I know it's 27 point something. 52 what? 521. Do we need units with that? Centimeters squared. Nice work. Very nice work. Number 5? Absolutely. Number 4, by the way, is all of this stuff right here. So we did one just like number 4, but we added an extra step to it where we found the circle and then we minused it. All right, number 5. The area of a rhombus. Ooh, what is the area formula that we know for a rhombus? Yes, 1/2 diagonal 1 times diagonal 2. This is another one of the formulas that you have to know for tomorrow. I will not give you this one. I'm giving you regular polygon, area of a sector, arc length of a sector, and I'll be real nice and throw in that second triangle area formula. That 1/2 AB sine C. I'll give you that one too. All right, they tell us that the area of this particular rhombus is 342.5 square feet. So that's going to go in for A, 342.5 equals 1/2. And then what do we know about the diagonals? One is quadruple the length of the other. What does quadruple mean? 4 times as big. So one of my diagonals, I don't know how big it is, so I'm going to call it X. The other one being 4 times as big should be called 4x. So I have 1/2 times x times 4x. I'm going to do 2 things at the same time in this next step. We're going to get rid of this fraction. How do we get rid of a fraction of 1/2? Multiply both sides by 2. 2 because it's the denominator. So that cancels my denominator out. I don't have a fraction anymore. That would give me 685. And then the other thing I need to do is multiply the x and the 4x together. What's x times x? X squared. So x times 4x would be 4x squared. I want to get the x all by itself. So how do I get rid of this 4? Divide both sides by 4. 685 divided by 4, 171.25. And then square root to find x. That'll make my squared and square root cancel out on the right. And we get a very gross number. 13.086 is x. So we're going to use that to find our diagonals. One of the diagonals is 13.086, but we need to put units with it. Close. Just feet. Why is it not feet squared? Because it's not area. We found one of the diagonals, which we would measure in linear units, so just feet or just centimeters or just inches. For diagonal 2, what do I need to do? Yes, 13.086 times 4, which gives me 52.344 feet. All right, that is all we have time for. Answer key is already posted in Canvas. 3 of the videos are already up. I'm waiting on the other one to finish rendering. And then that one will go up as well. I believe, if I'm not mistaken, the only problem that is not covered in at least one of the videos is problem number 7, where it gives you the area of the circle. You have to use that to find the radius and then the diameter. That is on my answer key, but if you like to listen to me explain problems, every single one except number 7 is explained in at least one of the videos somewhere.